Hey everyone, and welcome to The Explainer. Today, we're zeroing in on an absolutely massive headache for IT support engineers. We want to give you a reliable, rock-solid workflow for fixing those incredibly elusive memory leaks. Because, let's be honest, if you've ever dealt with an application that just gets slower and slower until it eventually gives up and dies, well, you are definitely in the right place.
So here's our diagnostic roadmap for today. We're going to hit 1. The silent performance killer. 2. What is a heap snapshot? 3. The snapshot comparison workflow. 4. Reading the retention tree. And finally, 5. A real-world scenario with a leaking dashboard. We're going to take these invisible problems and turn them into totally actionable fixes.
All right, Section 1, the silent performance killer. Let's start by just acknowledging the sheer frustration of those ultra-vague IT support tickets. You know the ones I'm talking about. The classic, the app feels sluggish, or my browser's lagging. Now, you might be wondering, why exactly is a slow browser so much harder to diagnose than one that just flat out crashes? Seriously, it's a question that keeps engineers up at night, because when an app is just gradually degrading, there are almost never any obvious console errors waving a red flag at you. It's just quiet. Think about the difference here. A hard crash? That is loud. It throws explicit errors, it's dump stack traces all over the place, and it's pretty easy to spot in your logs. But a memory leak? That's a silent disease. It degrades performance slowly, quietly eating up the application's heap memory without giving you a single warning. The browser's automatic garbage collector is trying its best, but it just can't keep up because your code is still holding on to references it honestly no longer needs. I absolutely love this quote from our sources because it just perfectly hits the nail on the head. Memory problems differ from CPU bottlenecks. A slow function is annoying but predictable. A memory leak grows over time, causing crashes at 3 a.m. It is literally death by 1,000 cuts. The tab doesn't throw a neat little error, it just gets tired, gets sluggish, and eventually completely chokes the renderer process. Moving right along to Section 2, what is a heap snapshot? So how do we actually fight this silent killer? We need the right diagnostic imaging tool, and that brings us to the Chrome DevTools Memory tab. Our primary weapon here is the heap snapshot. The best way to think about this is like taking a high-resolution X-ray of the browser's memory frozen at one specific point in time. It captures the entire memory state, showing you exactly how memory is distributed among all those JavaScript objects and the DOM nodes they're tied to. It's a complete picture of what's going on under the hood. Now, there's a really crucial distinction to make between the two main metrics you'll deal with, shallow size and retained size. Shallow size is just the memory held directly by the object itself. It's direct weight, basically. But retained size, that is the heavy baggage it's keeping alive. It's the total memory that would be freed up if that object and everything entirely dependent on it were deleted. When we're hunting for leaks, retained size is almost always where the biggest clues are hiding. Oh, and here's a super important detail to keep in your back pocket. Whenever you take a heap snapshot, the V8 engine automatically forces a garbage collection cycle first. This is amazing because it means your snapshot isn't going to be polluted by transient, uncollected junk. You're only looking at the active objects that are genuinely, truly stock in memory. Okay, Section 3, the snapshot comparison workflow. Now that we have our X-ray machine powered up, let's talk about how to use it to run a classic before and after experiment. We use a very strict 4-step loop to isolate the specific objects being created but never cleaned up. Step 1, get your app to a nice stable state and take a baseline snapshot. Step 2, perform whatever action you suspect is causing the leak, like, say, opening a modal, and then revert it by closing it back up. Step 3, click the little trash can icon in DevTools to manually force garbage collection. Step 4, take your second snapshot and pull up the comparison view. The real secret here is that finding leaks isn't about staring at a massive static pile of memory. It's all about observing the delta, the exact changes between those two interactions. In the comparison view, you want to zero right in on the size delta column. You are actively hunting for large positive values tied to objects that were supposed to be completely temporary. Basically, objects that snuck in between snapshot 1 and snapshot 2 but refused to leave. Which brings us to Section 4, reading the retention tree. Once you spot a suspicious object, you have to figure out why it's stuck. So let's shift to interpreting these X-ray results using the object retention tree. Chrome DevTools makes this a lot easier with some fantastic color coding for DOM nodes. Yellow nodes, those have a direct reference lingering somewhere in your JavaScript code, maybe a forgotten global variable or an old event listener. Red nodes are what we call detached. They don't actually have a direct JS reference themselves, but they're being kept alive entirely because they belong to a parent tree anchored by a yellow node. Think of the yellow node like a heavy boat anchor that's preventing that whole red tree of elements from drifting away and being cleared.
So, when you're digging through that retainer's pane, trying to find the root cause, remember this golden rule. Always, always look for the object with the shortest distance to the window root. That distance metric literally tells you how many steps away the object is from the global window. The shortest path is almost guaranteed to be your primary culprit. If you fix that, the rest of the garbage just naturally falls away.
All right, Section 5, Real Scenario Dashboard Leak. Let's put all this cool theory into practice and apply it to a concrete mock IT support ticket.
So here's a classic user complaint. You get a ticket that simply says, the analytics dashboard completely freezes after 30 minutes of use. Oof. According to our sources, this is a very real-world nightmare. It's usually a heavily used single-page application that looks perfectly fine at first glance, but is slowly eating up over a gigabyte of RAM until the tab just violently gives up.
So let's troubleshoot this in Chrome. You could easily replicate this yourself with a simple demo page using just a few lines of JavaScript to create a known leak. But here's how we tackle it. First, we open the dashboard, let it stabilize, and snapshot 1. Then, we play the role of the end user. We aggressively open and close multiple data widgets, maybe 5 to 10 times, to really amplify that leak and make it obvious. Next, we hit that DevTools trash can to force a garbage collection, sweeping away any normal, temporary data. Finally, we take snapshot 2 and jump straight into the comparison view. In a scenario exactly like this freezing dashboard, the culprit is almost always something called a detached DOM node. It's basically a ghost element. Visually, it was removed from the document tree the second the user closed that widget. But behind the scenes, it's being kept alive in background memory by a forgotten JavaScript reference. More often than not, it's an event listener that no one remembered to remove when the widget was unmounted. And guys, here is the absolute best, most powerful UI trick to instantly identify these leaked elements. When you're in the comparison view, just go straight to the class filter input box and type the word detached. If you see entries pop up labeled detached DOM tree with a large positive size delta, well, you've just found the smoking gun that's keeping those old widgets alive and freezing your user's browser.
By really mastering this before and after comparison workflow, you stop guessing about performance and start clinically proving exactly what's broken in the code. So I'm going to leave you with a question to ponder today. What invisible memory leaks are silently degrading your application's performance right now? Go boot up Chrome DevTools, take a baseline snapshot, and go find out. Thanks so much for hanging out with me on this explainer, and hey, happy debugging.